Go live.
Okay, we're live.
Okay.
We'll just wait for a minute. Let people join. And then exactly at 3, we can start. 1 minute left. Right? Now we have a viewer. We can go ahead.
Is the audio a little better?
Yep, a lot better.
Okay.
Cool. I'll drop off from the call then. We can continue.
Sure.
All right.
Okay. Bye-bye. Okay, I think we are good to go now. So, okay, I think we are good to go now. Yeah, the audio is working fine as well. Cool. So, hi everyone, and welcome back to the second live session on the real world assets series. So, in the last live session, which was last Friday. If you haven't checked out that yet, you can go on to QL Academy's YouTube channel, and there under the live section, you can go and check out the live session there. There we had gone through the whole repository. Uh, there we had gone through the whole repository. We explained where all the theoretical concepts what are so let us have a brief recap of everything. So yeah, we explained, we understood what are RWAs. We then understood how RWA is being applied onto the blockchain, what are the different types of RWAs, and then what are the key components and considerations when we are developing RWAs or when we are tokenizing RWAs. And then we went through the categorization model of RWAs. What are the different categories? How can we divide and how can we differentiate between different RWAs through their asset locations, the collateral location, and the backing type. And then we went through the mostly used categories of RWs in today's time, and went through some of the examples. And yeah, so we stopped and we left like we stopped the live session last time here. So from this in this live session, we'll be going through the whole tokenization process of an Apple share. So we'll be using oracles and we'll be using the Chainlink Oracle's contract. We'll be developing a whole contract from scratch. We'll be creating a whole the whole project. Then we'll write deployment scripts as well. We'll write a few unit tests as well. And then we'll also go through some of the security and auditing processes and auditing concerns which we should keep in mind while we are tokenizing real world assets. So if you have not checked out yet, there's a new section added onto our RWA repository, which is this auditing process for tokenization of real world assets. So in this, we have explained what are the key points and what are the main things which you should focus on when you are developing RWAs on chain. So we'll go through them later as well once we are done with the contracts and all. And I'll also explain some of the security concerns and security issues which you should have in mind. And yeah, So let's get started. First of all, I'll go on to my terminal, create a new project called Apple Apple RWAs. Okay. Cool. So if you want, you guys can follow along with me, and if not, you can just understand what we are doing here, and later you can use this live session, which will go onto a page after it's finished, and from there you can follow along from that video as well according to your own speed. So yeah, so this will be a very interactive and kind of, I'll not be just doing everything on my own. When there will be points and there will be moments where I'll get stuck as well. So we'll go on to the Google. We'll use AI as well. We'll be using ChatGPT. We'll be using Google, and we'll expand our knowledge horizon together while we are developing this. Okay, so let me just open the terminal, and we'll be using Foundry for this project. So let us go Forge NX. Okay, what is this now? Mm-mm-mm. Yeah. So we are using the okay. So let us first go to no. Yeah. So let us also to Foundry book. So you can go on Google and search for Foundry book. Here you will get all the information and everything related to Foundry. It is very well explained here. So you will go to installation, and here once you've installed the, like, you have to go open a terminal and run this following command. It will install Foundry into your system, and then after that, like, follow all these steps and all. And then once you're done, we can go on to first step of Foundry, and then you can initialize a new project from there. So we use Forgenet to initialize a new project in our in the specific directory in which we are in. So let us first see what is the whole framework, like what are the main files and what is the file structure of our project for now. So we have a library which includes all the Forge. It is a library for the Forge functions and commands, and then we have a script folder, we have a source folder, and then we have a test folder. So for now, let us just delete everything because we'll start fresh. Uh, okay, so first of all, let us go on to the source, and here we'll create the AAPL.sol contract. Okay, so okay, so SPDX license, prime authority, and just okay. So let us first write a few comments and let's understand what we are actually doing here. So we are what we are okay. So GitHub Copilot has generated something for our own. So We'll come to that later. So what we are doing is that we are using, we'll be tokenizing an Apple share, which is if we go on Google and we write Apple share. So you can see that currently one Apple share is worth 169.89 US dollars. So what we'll do is that we'll create a token, or we'll create an ERC20 token which will be pegged to the real time value, or the real time price of the Apple stock in the US stock market, and which will be backed by Ethereum collateral. Uh, yeah. So this is what we'll do. So if you go to the QuillAudits repository, and if I go to the source part and I click on the Apple.full, let us just get this whole thing from here, right? Okay, right. So the title is Apple.full, which is tokenization of Apple shares. So this is a token each representing an Apple share with the properties which are exogenously collateralized, Apple share pegged, and algorithmically stable. Why is it algorithmically stable? Which because we'll be writing code and algorithms which will keep the coin stable. And exogenously means that it is an Apple share, but it is backed by the Ethereum collateral. The backing type and the actual real world asset, the type of the real world asset and the type of the backing, which is backing the asset, is not the same. So in this case, this is called exogenously collateralized. These terms we had used in the previous slide. If you're not familiar with these terms, I'll request you to go back to that session and first go through that and then come on to this session. And yeah, so our session should always be over collateralized, and at no point should the value of all collateral be less than the dollar backed value of all the Apple. And the code base will mint Apple based on the collateral deposited into this contract. In this example, Ethereum is the collateral that we will use to mint the Apple coin, right? Okay, so let us write its contract. Apple AAPL is ERC20, and before that, we will have to import ERC20 here. Import, okay, nice, ERC20, and yeah, so here, as you can see, we are using Oracle library for aggregator v3 interface. So what is Oracle library? We'll go through that later, and these are the errors and everything. And yeah. So for now, let me just you know get these two addresses, and I will be explaining why I'm using them and all. And yeah. Before that, prior to that, let us just get these mappings. Okay. So we are using two mappings here, which is the first one is an address to UN256 called synthetic apple minted per user, and then we have a mapping from again an address type to Ethereum collateral type to Ethereum collateral, which is UN256, and here it is named Ethereum collateral per user. So basically, these are two mappings which we are using. In the first one, we'll be storing that how much an address or a person has minted for the Apple token which we'll be creating, and the second mapping is for that how much a person has deposited collateral. Right, right. So just a second. Mm-hmm, mm-hmm. Uh, let's just remove this. Makes sense. Oh, so majorly, if we go back to our repository, we could just duplicate this. And here they go on to the okay. So let us just focus on this diagram for once because this will give us a very brief and good idea, and it will make things a lot more clear and will bring clarity onto like how should we go on with our project. So in the AAPL in the AAPL dot soul contract, there will be a constructor, there will be errors, there will be external functions, then there will be public and view functions, and then there will be private or view functions. First of all, in the constructor, what we are doing is that we are initializing the Apple token contract with changing price feeds for AAPL, which is the Apple stock, and the Ethereum to USD, Ethereum USD price feed. And then we have the errors where we put the errors. Then we have the external functions. So these are the two very two major and the two main functions which we'll be creating in this contract. First one is a deposit and mint, in which firstly we'll deposit, in which we can deposit ETH as collateral and mint AAPL tokens, ensuring over collateralization. And how we are ensuring collateralization, we'll go through that when we are writing the contract. And then we have the redeem and burn function in which burns APL tokens and returns the Ethereum collateral to the user, maintaining the hash factor. So basically, what we are doing is we have a contract. So let's just say that if we create a front end for this at some point of time, then there will be a option to deposit Ethereum collateral. So we'll go on to the deposit button, and it will connect to our wallet, whatever it is, MetaMask or anything. And then let's just say that if I want to mint $100 worth of Apple tokens, so I'll have to deposit some amount which is more than that of $100, which I'll explain that how we are collateralizing. So for now, let's just take for example that if we want $100 of Apple token, then we have to deposit $150 of Ethereum. So once the transaction is done, then the Apple tokens for $100 will be minted, and once they are minted, we have those tokens. And let's just say that after a few weeks or after a few months, you want to get back your Ethereum collateral and return those Apple tokens. Then you can come to the website or the front end again, and then you can go on to the redeem section, and then you can redeem and burn. So what that will do is that once you click on the redeem section, it will return your collateral and it will take your Apple tokens and it will burn the Apple tokens and the collateral which you had deposited earlier, which was $150 worth of Ethereum, and you will get that back. So these are the two main external functions. Then we have the public view functions, which is which are get health factor, get USD amount from AAPL, which will convert Apple tokens to the USD value using the Apple price feed. Then we have the USD get a USD amount from ETH, which is the same function just for Ethereum. And then we have a Ethereum amount for USD, and then a get a account information value. And then in the private and view function, we have two more functions. So what is health factor and how we are doing it? We'll go come to that when we are writing the contract. So yeah, I guess we are done. So let us get back to the contract. So we have created the mapping, and then if I come back here, as you can see that we have a constructor right here. So let us just not copy. Let us just create a constructor which will take in address here and address of the Ethereum USD feed and ERC query, and here we will have to specify the name of the token which we are using and the abbreviation which we are going to use it. So here we'll name it as synthetic apple, and the abbreviation which we'll be using is AAPL. Then inside the constructor, we'll be initialize the contract with the price of Ethereum with the price feed addresses of Apple and Ethereum. So if I go on to here, then we'll have two addresses, which is address private uh, mm, I Apple feed, and then we have an address private I Ethereum USD feed, right? What we'll do in the constructor is that we'll initialize those such that I Apple feed is equal to the Apple feed, and the I Ethereum USD feed is equal to the Ethereum USD feed. Uh, okay. So we'll just write the comments here, which is we have the mapping to keep track of AAPLs. Let me just see if everything is going all right. Uh, okay. So we'll just write the comments here, which is we have the mapping to keep track of AAPLs. Let me just see if apparently everything is going all right. Fine. So we are done with the two addresses, which were for the Apple feed and the Ethereum USD feed. Then we have initialized them in the constructor as well, and then we have also created the two mappings which we are going to use. And yeah, so let us now go on to the first function, which is deposit and mint. So, so in this we'll be taking how many tokens we wish to mint, and what is the external variable, and yeah, what is this? Okay, so let's just understand this function right here, and then we'll start coding it. Okay, so what is this deposit and mint function doing? As I explained earlier, deposit and mint function is taking as a parameter the amount to mint. So we are taking in here how much amount of Apple tokens which we want to mint, and then it will be external and payable. Why would it be payable? Because like right here, it is not required to be payable, so we'll just omit that while we are writing, and then we'll be the message. Yeah, okay, so yeah, it is payable actually because we are using the message dot value here, so it has the function has to be payable, and then we are adding the health factor, get to health factor, and yeah. So before we go on to the get, like before we go on to the get health factor and all, let us just see what actually is health factor. So we'll go on to our way. Hmm. I'm just looking for the formula because which was so a health the health factor is a term which is defined by the RWA protocol. If you do not know about them, RWA protocol is one of the biggest DeFi protocols right now. Uh, okay, I think I'm not able to find that for now. So never mind. We'll just go on to a repository. And here, if I go on to the calculate health factor function, right here you can see that in the calculate health factor, so we are calculating the health factor by using three or four terms. The first one being collateral adjusted for the threshold, which is collateral value in US dollars into the liquidation threshold and divided by the liquidation precision. And then we have the collateral adjusted for threshold into precision and the Apple minted value. So why are we using collateralization here? Uh, why we are using over collateralization? Let me just remove this for a second and I'll explain this further. So let's just say that I deposited $100 of Ethereum to mint $100 of AAPL, right? In this is the case where there is no over collateralization, and the collateralization is as the same as the amount you want to mint, right? So let's just say that the value of Ethereum, like when you deposit $100 of ETH, let's just say that Ethereum fell by a lot, and the value of $100 of Ethereum has now depreciated to $50 of Ethereum. So now in such case, what is happening is that we deposited 100 Ethereum at that time, but now our collateral has now turned back to $50 Ethereum. So this is something in which the protocol will face the consequences and the problems because the person who minted $100 of Apple he has them all and there is no depreciation in the value of the Apple stock, right? But the collateral which is deposited to the protocol, which in this case is ours, what is happening is that we took $100 of Ethereum as collateral at that time, but right now it is worth $50 of Ethereum. So it is a huge loss situation for us now because we had given it $100 worth of Apple tokens, but now we are left with $50 of Ethereum, which is a straight 50% loss, right? So to avoid that, what we are doing is that we'll be creating a liquidation threshold or a collateral threshold in which if someone wants to mint $100 worth of Apple, they'll have to deposit of $150 worth of Ethereum, right? And even in such case, if the value of Ethereum even falls, let's just say that if it even falls to $125, still will be over collateralized and we'll have some collateral extra in this case. So this is why we are using over collateralization, right? So now what we'll do is that we will first of all create the view and pure function. So as I explained, we have get health factor, we have the get USD amount from Apple. Then we have to get USD amount from Ethereum, and then we have to get USD amount from US dollars. And then we have to get an account information value, calculate health factor, and get account information. Right. So, okay. Let us do one thing first. What we'll do is that we'll get all these constants copied, and then we'll have them in a contract. So now let us go through why we are doing that, why we are adding these constants right now. First of all, decimals, additional peak precision, and the precision. These three particular constants, we'll be using them to adjust the precision uh, of the USD amounts and everything which we'll be calculating. And why we are doing it? Because in Solidity, there are no floating number, right? So if just say that you have, if the answer is, if just say that 15 by 10, which is equal to 1.5, will be only equal to 1 in Solidity because Solidity cannot handle floating number, floating point integers. And in such case, it changes, converts it into the nearest integer. So that is why we have to use additional precision calculations to avoid that. Then we have the liquidation threshold, and then we have the liquidation bonus, the liquidation precision, and the minimum hit factor. So in this case, the liquidation bonus will not be using for now. Yeah. So the liquidation threshold, we are taking 50 for now, and why we are taking 50, you'll just understand that in a moment. Function deposit and the mint AAPL deposit and mint UN 256 and amount to mint which will be external variable and it will return nothing. Right. So in this function, first of all, what we'll be doing is that we'll be updating our mappings which we had just declared previously, which was implemented for user. So we'll just copy that, paste it here, and this would be message.sender, and this will be equal to the message dot value. So in fact, this will be equal to the amount to mint. What is wrong with? And then we have the Ethereum collateral, which will be message.sender, right? So first of all, we are updating two mappings which we had created, which first being the Apple minted per user, and we are taking the address is message.sender, obviously, the one who will be calling the deposit and mint function, and then we'll add the amount to mint which we are taking as a parameter to update the mapping array, and then we have the Ethereum collateral per user, which will be the Ethereum collateral deposited by the user in this particular function because this is payable. So message.value we are incrementing that as well, and then we have given 256 health factor, which will be equal to get health factor, and that we'll be putting the amount to, we'll be putting the message dot sender, right? uh then once that is done, I'm creating a if statement. If the health factor is less than the minimum health factor, revert health factor is below the minimum threshold, right? So then we can call the mint function, which is measures of center amount to mint, and then we are done for this particular function. So what we are doing is that first we are updating the mapping, then we are getting the health factor. This function yet not written, we'll just be writing that in a moment. And then if the health factor is less than the minimum health factor, so the minimum health factor is the constant which we had just defined, which is 118, which is 1 ETH. So that is something which is one we have defined. So if it is less than that, we have to revert by saying that health factor is below the minimum threshold. Then all the transactions will be reverted, and these mappings and everything will be reverted back to normal. And So if you do not know what the reward does is that everything which we had been executed in the function till now, everything will be reverted and it will go back to normal state as if nothing had happened and this function was never executed. Right. Then we are minting the message of sender amount to mint. And what is the mint function? If you remember, like we had declared that Apple is ERC20. So we are importing this ERC20 class into this contract. And if I go to the onto the mint function, okay, why is it not? Never mind. So what the mint function is that does that is that if we go on to ERC20 contract, right here, if you can see that we have a mint function right here. Function underscore mint, which takes an account as for the first parameter and the value as a second parameter. And what it does is that it mints that particular amount of whatever value which we have provided. It mints that particular amount of tokens onto the address account which we had just provided. So in our case, we the message of sender is the address to which we are minting, and the amount to mint is obviously how much he wants to mint, right? So let us for now first create the get health factor function. Function get health factor and this will take the address of the user and I go on to here. It can be in public function and it will be view only. It will return UN256. Right. So if I go on to our repository and then if you go to get health factor right here, you can stop with this and get this added here. So what we are doing in this right here is that we are getting get health factor. We are taking the user, that was the user as a parameter, and then it will be returning an UN256. So first of all, we are retrieving the account information into the total Apple minted value in USD and total collateral value in Ethereum value in USD. And we are using the function get account information value, which we'll just be writing in a moment. And then we are returning the calculate health fact using the calculate health fact function. So let us first create this get account information value function. If I go on to here, this is the get account information value function which we'll be using. Okay. So this is a function which is get account information value, where also one more thing, if you think that we are going a little too fast or a little too quick in this session, is because the reason that we have to cover a lot of concepts and a lot of points in this session, because we have to first write the contract as well, then we have to understand the deployment script and then the test, and then we also have to go through the added security part in a GitHub repository. So if you think that we are going a little slow, so what you can do is that you can after the live session, while you are going through, you can go through the session one or two times more, and you can adjust the speed according to your own understanding, and from there you can yeah, accordingly you can understand the concept. on your own pace, right? So the function can account information value, which is the address of the user. We are taking the address of the user, and it is a public view returns function. Also, one more thing, we have yet not imported Open Zeppelin contracts. So let us first do that first. So we'll do pose install Open Zeppelin slash pose contract. No comment. Now, why is this issue? No one, no problem. We'll go on to Open Zeppelin. Okay, my bad. It is double P instead of double L. I'm sorry for that. For install Open Zeppelin slash contract. Again, well, finally, it is not installing now. Uh, my bad. So the final command which you have to use is forge install Open Zeppelin slash Open Zeppelin hyphen contracts dash dash no dash commit. So don't be stupid like me and use the correct spellings and the correct commands. So we'll wait for it to get installed. Right, let's get back to this function right here. Yeah. So now we have quoted the open Zeppelin contract. Now if I click on to the ER70, I think it should open. It is still not. This sucks. So after compilation, I guess it will be there. Never mind. Yeah. So we right here we are using the get account information value, which is taking the address of the user as the parameter, and the public view returns, and it returns the total Apple minted value in US dollars and the total collateral value of the deposited total collateral value of the user in US dollars. So first of all, we'll be taking the total Apple minted and total collateral ETH from the get account information function, and it will be returning the values in native way values. So then will be also creating two more functions, which is to convert those values from Bay to USD, and the same will be done for the Ethereum collateral as well. So let us first create, create this get account information value. So if I go on to the repository, we'll take on the will take this from here, which and this page has pasted right here. So what the underscore get account information function is doing that what is doing is we are taking the address of the user, which is the private returns. It is a private function because we do not want it to be exposed to the world and be only for our use. It is again a view function itself. And yeah, so what it is doing, it is returning U256 total Apple minted and the total collateral leaf. So this is another form or another method of returning values inside from inside a function solidity. So either what I could have done is that I could have removed this right here, and I could have removed this and just specified the data type which I want to return, and then here at this function I could have written return and return here. Instead of that, what you can also do is that if you already know what are the variable names which you want to return, so you can just write them in the returns statement itself, and you do not have to then use the return keyword, and it will automatically those variables you can do all the computing in what you want, and at the end of the function, what it will do is that it will return the variable names which you have specified, which in this case is the total apple minted and the total collateral of each. So what is this doing? This is basically reading from the mapping which we are created, which stored the amount of apple minted per user and the amount of each collateral which is being deposited per user. So in this case, again, we are taking the address of the user. We are going through the array, and then once we find the map, once in the mapping we find the address corresponding to it, we will be returning the total the minted amount of apple minted per user and the amount of collateral per user. So once it is returned, let us come back to this. We are again storing that in a tuple. So if you don't know what is this, this is known as a tuple. So it is a custom data type in which you can just um, create two parentheses, and inside that you can include as many types of information or in any type of primitives you want to retrieve. So in this case, let's just say if I had an address blah blah here. So what I could have done is that I could have created an address here blah blah, and I could have stored or retrieved that address from here. So it doesn't mean that you only have to use Windows 56 throughout. You can change and use different types of data types as well. So just I'll remove this blah blah. Right. So I hope you have understood this get account formation part, that how we are retrieving the value. So now we have the values in way. Now our next step is to convert these values into their USD equivalent value. So we have two functions, which is get USD amount from Apple and get USD amount from each. So we'll just quickly go on to our repository and find these functions. So here there are these are the two functions which we'll be using. So let us just quickly copy them and add them onto our contract. So here what we are doing is that we are before moving on to this, as you can see, we are using the aggregator v3 interface, and to use this aggregator v3 interface, we have to use Oracle library for this aggregator interface. So we'll just do that. And before doing, what I want to do is that inside the source, I want to create a new folder called library, and inside the library folder, I'll be storing the Oracle library.source. The Oracle library.soul is a library which will be used to retrieve the different types of functions which are present in the Chainlink Oracle. So if we again go on to a repository, to libraries, inside libraries, if we go on to the Oracle library.soul, here you can see that we are importing the aggregator v3 interface from the Chainlink contracts, and yeah, we'll just copy this whole library file from here, and we'll be pasting that right here. Okay. So once this is done, just remember right now what is the aggregator we see, right? So let us just go on to Google and write a contract which is created by the team at Chainlink, which we have to use if we want to, mimic the Oracle actions and Oracle functions while we are testing or while we are deploying the contract in on onto a local host and a local development and local testing schemes. So in this case, if we have opened it, let's just go and into a test file. We'll include the mocks. Inside the mocks, we'll be creating add instead of that, let me just copy the name from here. Work v3 aggregator.sol and here, paste it here. We have it. Let me just copy this whole function from here and we paste that right here. So right here, we have taken this mock v3 aggregator.sol, and if you're not familiar with these concepts and these contracts yet, I'll request you guys to just go through the Oracle documentation one. And if you want to use it, we also will want to include the we'll also be want to include the chain link contract. Yeah. So we'll just import these as well. So I'm go like forge install and we can copy that. Never mind, I'll just install it through npm. We'll wait while that is getting installed. Oh, I think you guys are not able to see my terminal, right? I'm really sorry for that. I think now you'll be able to see my terminal. Okay. So what is the issue? Mm, Let me see. Why the hell is it not? Ah, oh God. Never mind. There is this focus on the development now. So we have created the Mock V3 aggregator, and we have also included the Oracle library into our in our libraries. What we'll do is that we'll go on to the what we'll do is that we'll be importing the Oracle library right here, and we'll be using that as the aggregator V3 interface. Okay, using Oracle library for aggregator V3 interface, and for the Oracle library, we will just import that. Mm, We can go to the store, copy this right here, and yeah. So we have imported the Oracle library and the aggregator V3 interface, and I think we are good to go again. So here we have created the get USD amount from Apple and get USD amount from each, the two functions. Now we'll go through how they are working, how do we intend to use it. First of all, in the first function we are taking as parameter the amount of Apple in way. So this will also be public view returns the function, and it will return a UN256. So first of all, we are using the aggregator V3 interface, which will create the price feed, and in the aggregator, and then in the aggregator V3 interface, we are giving the parameter as the I Apple feed, which is the Apple feed address of uh, Polygon mainnet. Share address on chain link. If you go on to Google and if you share that, if you search for that, and then if you go on to this particular data, where you can see that there's an Apple USD Apple to USD data feed which is available only on the net on the Polygon mainnet, right? So you have you can copy the contract address from here. We'll do that in the deployment script, that how we are including how we're getting this. We'll be going through that while we are deploying the contract. But yeah, for now you can go on to Chainlink and you can go on to data, and here you can see that there are a lot of things which you can use and which are very useful for developers. Also, you can go on to the search data and you can search for anything like let's just say you want to have the link token with value in USD. You can search for it, and then you have all the various chains from where you can pick up your contract address and use them in your development process. Right. So here we are doing the same thing. So we are putting in the address, the contract address of the Apple feed. Uh, then what will this will do is that it will create a local interface for the price feed, and then inside the price feed we are using stale check latest round data, which is if you go on to Oracle library.sol, and here if you can see that there's a function called stale check latest round data. So what this does is that at the time of when we call this function, what we'll do is that we have to give as input the aggregator V3 interface of the chain link feed, which we intend to grab the information from. And once we put the input at the time of calling this function, it will go and check the latest data of that particular feed which we're requesting. So in this case, which is the Apple share price. So when the function gets called, it will go on to its decentralized Oracle data feed and it will fetch the price of the Apple share at that moment and will be returning it. So that is what is happening in this. We are getting the price of the Apple share at that particular moment. And then what we are doing is that we are taking the amount of Apple in way, we are multiplying it with we are like, first of all, we are converting the price in which is currently a integer 256. We are converting it into typecasting it into UN256, and then we are multiplying it with additional feed precision, and then we are dividing it by precision. So let us now understand why we are using this additional feed precision and precision. So if I go on to additional feed precision right here, so these are the two constants which I had declared earlier, which is the first one being exponential, which is 10 to the power 10, and then we have 10 to the power 18. If you do not know about the E notation, so it basically represents how many zeros are there. So this is 10 to the power of 10, and this is 10 to the power of 18. So if we go back, you can see that we are multiplying and we are adding these constants for the additional precision due to the fact that I mentioned before is that there are no floating point integers, and Solidity has no methods to handle such floating point calculations. So in such cases, we have to use additional precision for that, right? So once that is done, it will return the amount of Apple, the amount, uh, the USD amount of the whole amount of Apple which we have minted, which we want to mint in fact. And then we have the same for the Ethereum, get USD amount from each. So in this case, what we are doing is that we have the Ethereum amount in there, right? So we are again using the aggregator V3 interface. We are using the Ethereum USD price feed, and then we get its real-time the price in US dollars. And if we multiply the price of one Ethereum into the if we multiply the price of one Ethereum in US dollars into the amount of Ethereum in which we want to be taking from the which we want to calculate, then it will return the value of the USD amount, value of the Ethereum and USD amount. So I hope these two functions are clear with you. Why we are using them, because we want to grab the real-time USD prices of the particular thing which we are minting and which we are depositing. So once that is out of the way, we can come back to our get and account information value. So now in this we have the total Apple minted value in USD and the total collateral value in USD by using the two functions. And then we can go back to our get health factor function, And here now we have received the total Apple minted value in USD and the total collateral Ethereum value in USD by using the get account information value, which is right here. Uh, yeah. Now, once that is done, then we are using the return calculate health factor, which takes in parameters two values in USD. So now we'll quickly go over onto our repository and get this function right from right there. So this is the function which we are using to calculate the health factor. Okay. So now what this function is doing is that once we retrieved all the values and everything in US dollar values, now what we want to do is that we want to calculate the health factor. So the health factor is calculated by using a formula which is provided in the documentation of Aave. So I've used that same formula for the calculation of the health factor. So the health factor, first of all, one may ask that what is this health factor thing and why are we even using it? If we just simply want to, just mint some Apple tokens and just deposit some Ethereum collateral, why are we even using this health factor thing? So we are using this health factor scenario, this whole health factor calculation thing, because we want our protocol to always be over collateralized. As I'd explained in the example before, that if this is say I deposit $100 of ETH and then it drops to the value of Ethereum drops, the price of Ethereum drops, and then that collateral value is now only worth $50 of ETH. And now in this case, the protocol is under collateralized, which we never want to have, which we never wish that it happens, right? So that is why we are using this health factor functions, and you'll get to know that later that how we are using this health factor thing. So we are taking in the parameters US the USD value of that total Apple minted and the USD value of the total collateral which the user has deposited. It is an internal pure function and it returns U into 56. So if Apple minted value in USD is equal to 0, then we can just return we can just return the maximum value which 2 into 56 and all. Why? Because if the user has yet not minted any Apple tokens, and so in that case, the health factor is maximum. So now the UN256, we are defining a parameter which is we are defining a variable called collateral adjusted threshold for threshold. And in this, what we are doing is that we are taking the collateral value in USD, which is this, and then we are multiplying it by the liquidation threshold, and we are dividing it by the liquidation precision. Now, what is liquidation threshold and what is liquidation precision? Let me just quickly go on to liquidation threshold. So this is a constant which is equal to 50, and we are using this constant so that our system is always over collateralized. So in this case, this means that you need to be 200% over collateralized, right? So if I jump back to where I was here, if I yeah, so the collateral value in USD we are multiplying it by 50 because in that is the multiple in which we want to have the extra amount of collateral. And then once that is done, we are multiplying it and by dividing by the liquidation precision, which is again used for the floating point precision. And we are returning the collateral adjusted for threshold, which is this in a variable, multiplying it by the precision because we had divided by the liquidation precision, so we have to multiply it now. And then we are dividing it by the Apple minted value in USD. So this is a formula which is defined in the way documentation. So feel free to go and check out that. So I'm using the same formula for calculating a health factor. So once the health factor is calculated, we can again go back to a deposit admin function. And here now we can see that all the functions are now created. Because first of all, we defined the get health factor function. We have written the health factor function. Inside that, we are using the get account information value, which is also defined. And inside the get account information value, we have three more functions, which is get account information, get USD amount from Apple, and get USD amount from Ethereum. Then going back to the get health factor function, then we have the calculate health factor, which is also defined here. So yeah, we are done with the deposit and mint function. Now, once the person has deposited and minted the amount of tokens he wants to, now he wants to now we'll add a function which will burn and withdraw, right? So if I just go and get this function right here. So this is the function redeem and burn, which we'll be using to for the user so that he can come and redeem his collateral and burn the particular amount of tokens. Sorry, the amount of tokens, right? So we'll just go through this function. We'll just take a short break, a quick break, and then we'll be going through this function for now. And once this function is done, I think we'll be done with the AAPL or soul contract, and then we can move forward to the deployment scripts and to the test. So we'll be back in 2 minutes. Alright, guys. We are back. So let us again continue with the yeah. So inside the function which redeem and burn, we are taking the UN250 amount to redeem, which will be an external function. So this will be the amount which the user wants to redeem back, the amount of collateral which the user wants to redeem back. So what we'll do is that we will first of all calculate the USD value of the Apple, the USD value of the Apple tokens to be redeemed, right? So the person what will do is that he'll in the amount to redeem thing, he'll put in the Apple tokens which he wants to give back to the protocol, and in return he wants back the collateral. So what will have to do is that when the amount to redeem is deposited, like the in, input by the user is given, we have to convert that particular value from way to the USD amount. So for that also we'll be using a function to for doing that, right? And then we'll have to calculate the amount of ETH to return for the redeem Apple tokens, which will again be done by another function which is called get Ethereum amount from USD. And once that is done, then we'll further make the changes in the mapping, and whatever we also have to update the health factors and all. So before doing all that, let us just simply go through the two functions and get them written. So if I go and get GST amount from Apple and get GST amount from Apple, right? Just a second. So if I go on to we have a USD amount from Apple, then we have the get USD amount from Ethereum, then we have the get Ethereum amount from USD, and yeah, that is all. Okay. So now the new function which we have just imported is the function get Ethereum amount from USD. So what it will do is that we'll use this in the redeem and burn function. So what we will be doing here is that it will be taking the USD amount of Ethereum. So it is doing the reverse which we were doing. It is doing the completely reverse of in this function. So previously, what we were doing is that we were putting the values in UA and we were getting the output in USD. So in this case, we are the input is the value in US dollars and the output would be the value in base, so that we can return the person how much the corresponding amount of Ethereum collateral which he has to get back, right? So that is what we are doing. So if we go back to this function, everything is just the same. Most of the things are same. We are again getting the USD price, but in this case, just the multiplication and division is different. So previously we were multiplying it right here with the price. Now the price has gone in denominator, and previously the price was in the numerator. So this is the only difference. because here we were calculating the values in USD and here we are calculating the values in whilst taking the input in USD. So I guess you must have understood the difference between the difference between these three functions. So basically, these two functions are same. These two functions are doing the same thing. This is doing for the Apple token, and this is doing for the Ethereum. And here we are doing this for the Ethereum amount to get that in way from the USD, right? So once that is done, we'll calculate the Ethereum, which the amount which we have to return, and then we will decrease the sender Apple minted amount in the mapping. So we'll just go to message the sender, and here amount to redeem, the total amount the total amount of USD tokens which we wanted to redeem. We'll just reduce that from the mapping, and then we'll calculate the health factor again. So if the health factor is less than the minimum, we will again revert the transaction. And this is an error, so we'll just go and add this error. And once that error is done, we'll then call the burn function. And if the burn function, as we have just seen, there was an underscore mint function in the ERC20 token standard given by OpenZeppelin. Similarly, there is a burn function as well. So we use that to burn the tokens, where the address, the message of sender is the address for which we are burning, and the amount to redeem is the amount of tokens which we want to burn, right? And then we have transferring the calculated amount of Ethereum back to the sender by using the Boolean function message.sender.call value Ethereum to return, which we had just calculated here. And if the transfer fails, revert the transaction. This is what we are doing here, right? Because it will return a Boolean success. So if the success is true, which means that the transfer has been completed, and and if it is false, which means that the transfer has failed. So we'll revert the whole function right here. So yeah, great. I guess we are done for the AAPL.sol contract, and we have written all the contract. I hope you have all the contract function and everything we have clearly understood and explained while writing this. Now I think we can go on to the deployment script. So if I go on to the script and deploy AAPL dot S dot so there's a storm right here in my city. So just okay. Never mind. Let's just not get distracted and focus on the deployment. So if I go on to the thing, also one more thing, since we have included some libraries, we also have to remap them. So I'll just go to the foundry.foundry file and just add a few remappings. Okay, so the remapping is done. So if I go on to the deploy apl.s.sol contract, right here, what we'll do is that will be there'll be two scripts which we'll be using, which is the first one will deploy apl.s.sol and the second would be the helper config, which we'll use to handle all the contract addresses and all from there. So what we'll do is that first we will go on to the helper config and get everything from there. So let us go on to the script, create another file called helper config.s.sol, and then we can paste the helper config. Also, if you're wondering where this all code came from, you can go onto the repository again, and then in the scripts we have the helper config.s.sol, right? So also I would have written this whole contract from scratch with you guys only, but since we are very short of time, and if I start doing that, we'll this live session would be go around 3 to 4 hours long, right? So there would be no person who would be willing to spend this much time. So you guys can I'll be explaining the whole contract line to line. Don't worry about that. But yeah, if you want to check out the contracts and everything, it is all there in the repository, and you can go and get that from there. Okay. Right. So now Yeah, so this is the helper.config.s, the script which we were talking about, and then we have the deployment script here as well. So first of all, we'll go to the helper config. So what we are doing here is that we are using the Foundry's script uh, tag which we are importing from Foundry. So what it does is that in Foundry everything is written in Solidity, and even the tests and even the scripts, everything is in the form of contracts. So to differentiate the contracts, if whether they are scripts or tests, there are libraries in Foundry which we have to import. So in this case, when we are writing a script, we are importing the script library, and we are using this. We are like contract helper config is script. So here we are using that. So yeah. So again, we are importing the mock v3 aggregator, which we had written in our mocks. We are importing the script as well, and we are importing the ERC20 mock as well, because we want to interact with the ERC20 functions and the ERC20 methods. So we also have to import the ERC20 mock. So contract helper config is script. So there is a network config. Which is a type of struct. So we'll be defining the struct right here. So a structs are basically modified data types where we can create data types of our own whatever we want. So right here, network config is a parent data type, and inside that it consists of three primitives, which is address, which are two addresses and one UN256. So the first one being the Ethereum USD price feed, the second one being the Apple price feed, and the third one being the deploy key. Here in this case, the deploy key is the local private key, which is given to us when the local blockchain is initiated, when we are using the local blockchain node, which is a feature available in Foundry. So you can use local blockchain development suites and local blockchain nodes to test your contracts and deploy them. So here we have this. This is the default annual private key, where annual is the default local blockchain of Foundry. So once the struct is created, we are creating a new type for network config, public active network config, which is of the type network config. And then we have Apple feed mock and the Ethereum USB feed mock, which are again of the type mock v3 aggregator. Then we have a constant decimal rate and a public constant, which is Ethereum USB price, 2000 E8. And then if I go on to my constructor, previously, as I told you, that the price feed contract which we are using is on the Polygon mainnet, right? And if I go onto the Polygon mainnet chain ID, it is 137. So 137 is the Polygon chain ID, the mainnet chain ID. So here in this case, if the block.chain ID, so this is the block.chain ID is the method which is used to retrieve the current chain ID on the blockchain on which we are working. So if it is 137, then the active network config will will be equal to the get polygon config, which is a function which we have defined later, and we'll go through that. And if else, we have to create a new annual Ethereum config, right? Where annual in this case is the local blockchain node which we are using. So in the get polygon configuration, what we are doing is that we are using a config, and this is the config which we are returning, right? So this config is also of the type network config, which we had just listed here, written here and defined here. So this is also the same type. This is the config which we are returning, and here we are doing network config is equal to, and inside this we are um, initiating the different values. So the Ethereum USD price here, right? So if I go on to here, and if I search for Ethereum slash USD price feed, and if I go to the Polygon mainnet. So this is the Ethereum USD price feed on the Polygon mainnet. So I'll just copy the contract from here, and it is already pasted there, so no need to be paste that. So it is the same, yeah, cool. So this is on the Polygon mainnet, the Ethereum USD price feed which we are going to use, and the Apple price feed. If I again go on to here and search for AAPL, So we have it on the Polygon mainnet and 0x7E7B, 0x7E7B. So this is also correct. So these are the contract addresses of the two price keys which we are going to use. And in the deployer key, we will be including the env environment variable, and we'll retrieve that from the private key. So this is a way to include the private key from the virtual machine. We'll not go through this right now because majorly we are going to focus on the local development, the local testing, right, local deployment. So if it is not on the Polygon mainnet, then we get or create a new annual Ethereum configuration. So in this case, we are again, returning a network config memory type named called annual network config. So here, first of all, we are checking if already there is already we have set an active network config. If yes, then we are returning that without anything and without making any changes. And if not, then from here we have to write the we have to create the Ethereum configuration and the network config struct ourselves. So first of all, we are doing VM no start broadcast. So onwards, every line onwards, this line before the stop broadcast line will be broadcasted onto the blockchain. So this the start broadcast and stop broadcast are two functions used in Foundry, where where any lines and any code written between these two methods are directly broadcasted onto the blockchain. So we are fetching the Apple feed mock from here, where it is new mock V3 aggregator. Inside that we are putting decimals and Ethereum USD price. So if I just open mock V3 aggregator here, so here we can see that it has a constructor which takes in decimals and initial answer. So for the decimal, we had already given the constant 8, and for the initial answer, we are using the Ethereum USD price, which is 2000 E8. So this is also default Ethereum USD price which we are taking for now. So this won't really matter because this is only because we are using the mock for the aggregators, and these are not the actual aggregators. When this will be deployed onto the mainnet and not to the local blockchain, then the actual V3 aggregators will be used. But in this case, we are only using the mock. Right. So once we get the Apple feed mock and the Ethereum USD feed mock, then we'll stop the broadcast. And then in the annual network config, what we'll do is that we'll create a network config as we created previously for Polygon mainnet. And here we are doing the Ethereum USD price feed, and we are taking in the address of the Ethereum USD feed mock, which we had calculated from which we had retrieved from here. And then we have the Apple price feed. Again, we'll be taking the address of this Apple feed mock, and then we have the deploy key, which is the default and private key, which we had already mentioned here. So yeah, I think we are done with the uh, deployment, the helper config or S4. So now we will be importing this helper config file into the deploy file. So if I go on to the deploy file and get that here, so in this case, we are importing the helper config and we are writing deployment script here. Also, one more thing: if you are finding all these concepts and everything too difficult to understand, I think you should go through the basics of Foundry once. Uh, there are a lot of good resources available on the internet for Foundry. You can go on to there are various YouTube courses, and you can also go on to Patrick Collins' website, which is called Cypher, and they have also created various courses and pretty good courses on Foundry. So you should go over them first, understand what is Foundry, how we write tests, and how do we write scripts in Foundry, and then we can come back and then you'll be able to understand what we are actually doing here, right? So yeah, so we were done with the helper config. So now we'll come back to the deploy script of the main deploy script. So again importing the script. We are importing the Apple contract itself, and we are also importing the helper config which we had just created. So just Right. So if I come back to the deployment script, so first deploy AAPL script, then we have a function run, which will actually do the deployment thing. So in this, we are getting firstly, we are getting the parameters, which is address of the Apple, sorry, address of the Apple feed and the address of the Ethereum feed, and the deployment deploy key using the get AAPL requirement function. So if we go on to the get AAPL requirement function, which is right here, here we can see that it returns address, and event total, exactly what we are retrieving here. So if we just say helper config is a new helper config, so this is where we are using the helper config. So once the helper config is a new helper config is initiated here, what we are doing is that we are fetching the Ethereum feed, the Apple feed, and the deploy key from the helper config dot active network config. So if I go on to helper config again, you could see that we had created a function. We have created a variable called the active network config, which is of the type network config. So again, we are calling that here, right? And this is what we will be using for fetching the Ethereum feed and the Apple feed and the deploy key. So once that is done, we'll go. If Apple feed is equal to, even after fetching, if the Apple feed is giving is being equal to or zero address, or even the Ethereum feed is being equal to zero address, then we can revert. And finally, if it doesn't revert, we can return the Apple feed from here, the Ethereum feed address from here, and the deploy key from here. Okay. So after that, we also have the function deploy APL, which takes in the Apple feed and the Ethereum feed, and it returns AAPL, where AAPL is obviously uh, the contract. So it returns a new AAPL, and what it does is that it deploys the AAPL contract using the Apple feed and Ethereum feed. And if we go into a AAPL contract, here you can see in the constructor we are using in the constructor there are two values which we have to which are being provided. The first being the Apple feed, and the second being the Ethereum USD feed address. So these two addresses are exactly being fed into the constructor while we are deploying. So we'll then start the broadcast using deploy key. We'll then deploy key is fetched from here. Then we'll use the deploy APL function, and Apple feed and Ethereum feed will fed into the constructors and stop broadcast. So this is how we'll be deploying our Apple .sol Apple.sol contract. So this was all for the deployment script and the helper config. So now we can go and move on to the unit test. So let me just create a file called unit, and inside the unit we can create a file called AAPL test.t.fl. So if you notice right here, when we were creating the script files, we were using a .s.sol, and when we are creating the test file, we are using .t.sol. So this is a convention, a naming convention, which a file naming convention which we use in Foundry to differentiate the script files and test files. So if it is a script file, we use a .s.sol, and if it is a test file, we are using .t.sol. So this is also one thing, good practice, which you should use while you're developing in on Foundry and when you're using Foundry. So even if you do not use these, it won't make sense in the functionality or in the execution of the contract or the project. But yeah, it is good practice to include such naming conventions. Right. So now, if I come onto the Apple test.t.sol file here, if you can see that first of all, we'll just use the ST here. Once that is done, then we'll be importing ERC20. No, we do not want ERC20. We want import test from forge stt slash test. Then we'll also import APL and we'll also import the deployment. Deploy AAPL from sometimes these GitHub Copilot suggestions are really shit. So you should not always press tab. First you should verify and then press tab. So never mind. We'll fetch that from not deployment, it is in script and it's from inside the script. We can go on to deploy apl.s.code. Done. So what is the issue? Oh, so it's still in the this is obviously not for std. I'm sorry. This would be dot slash dot slash src apl.com. What is the issue? Uh, it is currently here. So it will go out of this function, it will go on to the test.mocks, and then we'll also be going on to test.mocks. Then it will go on to the source, and as a source, it will go for the APL source. And for the deploy APL, it is currently in the unit. It will come out from here, test.mocks. It will also come out from here, and then it will go on to the script and deploy APL.s. I have no idea why this is. Uh, Never mind. So now contract AAPL test is test and AAPL uh, AAPL. So we are creating a AAPL type of we are creating variable called AAPL, which is also contract type AAPL. Then we'll also have deploy AAPL deploy AAPL. So here we are using a deploy APL type. Uh, we are creating a copy of the deploy APL type and storing it in deploy APL. And then we have an address public user, which will be equal to make address name being user. Right. So again, if this is all very new, or if you guys have not, if you guys are not understanding what is happening here and what is this make address and everything, so I'll again suggest you guys to go to Foundry documentation and see a few tutorials on Foundry. Build a few build one project on Foundry, then you will be able to understand why how the tests and scripts are being written. And if you already know, then you obviously just follow along with me, right? So instead of writing this whole thing here, what I can do is that I can go on to this and I can paste it here. right? So now I have the whole thing mentioned. So I will go through all the lines and all the functions and what is exactly happening here. So first, deploy APL, we are initiating it, which is of the type deploy APL, which is obviously the deployment script of the contract. And then we have the AAPL, which is the of the type the AAPL contract, which we have imported here. Then we have address public user, which is make address. So this will create a new random address, uh, and we can pass in anything here. So this will just make a new address. Then we have a unit constant, which is starting Ethereum balance. So we are like creating a constant that we have the starting Ethereum balance of 100 each. And then there's a function setup called where we are using the deploy APL and we are initiating it by using the new deploy APL right here. And then the address APL field and the address Ethereum field we are retrieving from the deploy APL.getApple requirement. So deploy APL is of the type deploy APL, which is obviously the deployment script. So if I open the deploy APL.s.source file, and here we are using the get Apple requirement, right? So if I go on to this contract, get Apple requirement, so it is what is it returning? It is returning the address of the Apple feed, the address of the Ethereum feed, and the Unit56 deploy key. So here what I am doing is that uh, we are retrieving the address of the Apple feed, the address of the Ethereum feed, and we do not want the private key here, so we are not retrieving it, right? So once we have the Apple feed and Ethereum feed addresses, what we can do is that we can again call on Apple, and what it will do is that deploy APL dot deploy APL Apple feed and Ethereum feed. Again, if you want to deploy APL, there was a function called deploy APL, right? So here we had to put in input as the Apple feed and Ethereum feed. So that is what we are doing here. So once that is done, the setup is completed. And now what we can do is that we have to test the deployment of APL, that whether we are able to deploy it or not. So what we'll do is that we are using this function test deploy APL public deploy APL dot run. And again, if I go to deploy APL, there was a run function which is doing the actual deployment, the actual and final deployment. So if it passes, then obviously the test will pass. So this was a test for the deployment. Now then we have a test which is called can mint APL. So here we are testing that the contract which we have written, whether it can mint the Apple ERC tokens or not. So again, we are using the vm.deal user starting VM balance and vm.frank user, and we are using apple.deposit and mint. So we are retrieving the function from the Apple contract, which was a deposit and mint function. And here in the parameters, we had to input the amount to mint, right? So here also what we are doing that we want to um, like mint this amount of value. We have to mint this amount of ERC20 tokens, and the collateral which we are providing is this 10 and then assert equal apple dot balance of user should be equal to 118. Why? Because uh, balance of is obviously an ERC20 function where we can use that balance of function to, and we'll provide the address of the user, and it will give us the value that how much is the balance of that particular token. So in this case, which is the AAPL, which is the Apple token, the Apple ERC20 token. So it will give back the balance which the user has of the Apple 20 token. Right. So again, try to understand. Here we are using the ERC20 token method where the balance of function takes in as the input as the address of the user, and it returns the balance of that particular token on which the balance of function is called, which in this case is the EAP ERC20 token. And that should be equal to 118. Why? Because here we wanted to mint 118. So this should be equal to that, right? And then the mint, if when we are checked, then we'll again write another function where the test can redeem. So the mint function has been tested. Now we'll have to test the redeem function. So in this case, uh, We are again VM.deal, user starting Ethereum balance, start rank, stop rank. If you are not aware of what is the start rank or stop rank, I advise you to go to the documentary of Foundry and then you'll be able to understand what is happening here. So these are basically different commands which we use in whereby we are testing smart contract functions uh, in the test files, in the test contracts in Foundry. So here we are again calling the deposit and mint function, and now we are minting 180 118 amount of ERC20 AAPL again, and then we are approving. Approve is a function which is again defined in the ERC20 token standards, where we approve another address to spend on our behalf. So what it can do is that instead of us making a transaction or making any payable transactions from our end, we can approve another address to make that transaction on our behalf. So we are approving the address of the AAPL smart contract, and we are giving the AAPL smart contract the authority to spend uh, um, on our behalf. So then, and the value also defined that we are approving the address. We are approving the Apple smart contract, which we had written here. We are approving the smart contract to spend on our behalf, and the maximum value on which it can spend is 180. So then we are calling the redeem and burn function, which we had defined here. And inside that, we have to, in the parameters, we have to input the amount to redeem, right? So in the amount to redeem, we are again, since we had minted 118, so we also have to redeem 118 itself. And once that is done, then we'll stop the tank and assert should be equal to apple dot balance of should be zero. Why should it be zero? Because initially when we had minted, the balance was one. And now once we have burned, because when we are redeeming, automatically the ERC burned. So now the balance of the user hundreds or more of tests. You can write a test function for anything, and there could be there could be other types of tests as well, which are first tests and all. So we have not included those in this repository because this was a repository which was aimed at beginners who are just dwelling into the RWA world. But yeah, these are some of the tests, um, how you can write them, and just for the understanding. So I think we are done for the most of the coding part. Now what I will do is that I'll just close this and I'll wait, uh, yeah. So once all the tests and everything are written, we can. So this is the same code base which you guys can go on to GitHub and clone from the real world assets from a real world assets repository. You can go on there and you can clone this and run the tests and run the deployment scripts uh, on your own. So we'll just do for if you're wondering what functions can be run using Foundry, then you can just write forge help and it will give out a list of all the commands which you can use. So in this case, what we'll do is that we'll be using the forge test command. So we'll go on to forge uh, test, right? So it will run the test, it will compile, and then you can see that ran three tests for the test AAPL test e.source and test convent APL. It is also passing, and the gas which is being used in that function is this much. Then we have the test can redeem. This is also passing, and then we have the test deploy APL, which is also passing. Um, if one more thing, if I use boundary coverage, oh sorry, forge coverage. So what it does is that it will first of all compile all the files which we have in our project, and what it will do is that it will give all the coverage information for all our contracts which we have written. So this is also something which comes in handy while we are testing our contract. So I think we are done for most of the part. Now, before moving on to the security aspects which we have just added onto our GitHub repository, I'd like to mention one thing that in our AAPL.soul contract, the two main functions, are deposit and mint and the redeem and burn. So here, first of all, to avoid re-entrance attacks, we should always follow the checks, effects, and interactions pattern, which is, let me just write that, checks, effect, interaction, right? So first, you should always do the particular checks, then all the effects in the states should be done, and then the interactions with an external contract should be done. So this is one pattern which you guys should always follow when you are writing smart contracts. So for better understanding, let us just go on to checks, effect, interaction, pattern, solidity. Here we have it. So the intent is to reduce attack surface malicious contracts. So the implementation is that to implement the check effects interaction patterns, we have to aware about which parts of our functions are the susceptible ones, right? Once we identify that the external call with its insecurity regarding control so is the potential cause of vulnerability, we can act accordingly. So in this sample code, the user balances are stored in a mapping in line 3, right? So there's a function deposit called. And what we are doing here is that the deposit function in line 5 lets the user deposit ether in the contract and stores the respective balances. The actual pattern is implemented in the withdraw function in line 9, right, which is provided with the amount requested to withdraw. First, the first step is conducting all necessary checks. As this is a small example, there is only one condition to check. So, yeah. So here in this function, you can see in the withdraw function, we are following the checks, effects, and interactions pattern. So first of all, we are checking. So we have first of all we have all the required statements and everything which we need to check before moving forward with the execution of the function. So we have first of all we have the required statement which is checking, and then the next step is the application of all the effects. After that, the all the effects to the state variables and everything should be done. After we are done with the checks, now it is time for the effect. So now once the effects are also done, then only we should move on to the interaction, which is all external interactions take place in the last step. So here, once everything is done, now the message to send it transfer amount, then we can transfer the amount which we wanted to, which the user wanted withdraw, right? So let's just say in this case, if this message dot sender line, if this line was before the balances line, so what could have happened is that a hacker, a malicious actor could have exploited this function by again and again calling this function, right? Since because this line is before the balance updating line, what would have happened is that if a person again and again executed this line before moving on to this line, then what would have happened is that since the mapping is yet not updated, the value would have transferred again and again without reflecting on the balances mapping. So these are called the re-entry attacks, and to avoid them, we use the CEI, which checks events and interactions pattern. So I hope you have understood that, and then I think we can move on to our repository. So this is a new part which we have added in the repository, and I request you guys to go through it because it is quite important, and we'll also go through this quickly uh, in the session as well. So tokenizing real-world assets on the blockchain involves creating digital representations of physical or non-physical assets, right? So this process requires rigorous security, legal compliance, and accurate representation of asset values through reliable data feeds. So, what are the main steps we should be following? The first is security audit. We should obviously have code reviews, and we should also have the architecture review. Uh, and then we also have the Oracle reliability and data integrity, the Oracle choice and implementation. Since in real world assets, in the tokenization process of real world assets, it is very necessary and it is inevitable not to use oracles. So we have to use oracles, and for the proper usage of oracles, we have to evaluate all the oracles and the data sources which we are using, that whether they are truly decentralized or there could be any possibility of any bad actors there. So this is one thing. Then we should also have some fallback mechanism, which is assessment of mechanism in place for handling oracle failures. So let's just say an oracle failed and you are not able to retrieve your data feed. So in such case, you also should have the fallback mechanism. Then obviously we have the compliance and legal reviews because when we are tokenizing real world assets and we are bringing in them on chain, let's just take for example, let's just take example of real estate. So real estate is something which is heavily governed by regulatory and government policies. So before getting them on chain, before tokenizing them, we should also be widely knowledgeable about what the compliance and legal issues related to them. Then we have the function testing, where we should write detailed tests for each function to ensure that they perform as expected, which we just did. We wrote a unit test. And then we should also use the integration testing, which is testing the contract's interactions with external contract and services like Oracle. And then we also have scenario testing. Other than that, we also have the performance and gas efficiency, because obviously we should always write smart contracts and we should always optimize the smart contract such that it uses the least amount of gas, and it should be very gas efficient. And then we have the user role and access control. So in this particular, the permissions and roles of all the functions and everything that who like every function cannot be executable by everyone who's using the protocol. Right? There are some functions which are permissions, so we have to assign the proper roles and do that. So if we come on to the specific audit of the provided smart contract, so specific audit of the contract which we have written. So in this case, we had to write the security audit where the functions deposit and mint and redeem and reborn functions are susceptible to the reinstallation attack, right? Especially since they involve transferring Ethereum. So this should be mitigated by using a check event interaction pattern. So this is something which I'll leave you guys for. You can go through the deposit and mint and the redeem and fund functions, and you can go on to them and see if the CEI pattern is implemented or not. If it is not, then you're free to create a pull request and make changes in the contract. That I would love that. And then again, we have to see to the compliance and legal reviews, right? And in this contract which we had created, the contract meant token representing app shares of Apple, which are obviously security. So this requires compliance. So since this was an example smart contract which was also only made for educational purposes, we did not take into account the compliance and legal reviews and everything. But if someday if anyone they are pushing it onto the main list, and if they are actually implementing those projects, then this is something which they have to go through. Then we have the functional testing again, and the gas efficiency, and then the user and the access control. And then we have the integration of first testing in all the process. Now, first of all, let us understand what is first testing. I'd like you guys to put some attention here, because first testing is very important nowadays, and it has now become the baseline for testing. So the purpose of first testing is critical for identifying hidden issues that are not obvious during regular testing phases. It helps in detecting vulnerabilities like buffer overflows, crashes, memory leaks, and handling of unexpected or malicious input. So first testing is basically testing